what I want to do is start creating some live lecture video content on topics that I'm interested in, and also like I feel I understand well enough to kind of help others understand. And I know there is a lot of content out there on various topics that I am familiar with, but I feel like I can add a different dimension to that. Uh, so first of all, the topics that I'm interested in are uh, mostly in the domain of computer science, but I like thinking and studying theoretical aspects of computer science. So my interests are, first of all, algorithms, theory of computation, distributed systems, and also recently machine learning. So my content is going to focus on diving a bit deep into foundations of these areas. So mostly theoretical results in distributed computing, machine learning, and also algorithm design. So that's the plan, and I think the first videos may be rough and may need formatting and updates, but I'll try to make sure that they get refined over time. So what I want to do is share my screen and OneNote page. So hope this is visible. So as I mentioned, kind of machine learning, kind of distributed systems, and kind of algorithms. So these are the topics we'll cover. Uh, so I know everyone is really interested in machine learning, and there are a lot of video series on like practical aspects of machine learning. How do you start coding? How do you start using large language models and other AI tools that are out there, agentic systems? But I want to focus on the foundational topics, starting with machine learning and also deep learning. I've recently taught a course on foundations of neural networks at a local university, and I might reuse some from material from there. Uh, on distributed systems, again, that's a very practical area, and distributed computing is kind of the backbone of cloud computing systems like AWS, Azure, GCP. Uh, my training in distributed systems is more formal. That was the area of my PhD, and we did learn a lot of theoretical algorithms, uh, impossibility proofs, which seem arcane and may not always seem useful in practice, but they are really important to understand kind of the trade-offs of distributed systems. Like nothing is ever free. Like if you feel that a service is free to you, there is always some hidden cost. So one aspect of these theoretical results is to kind of understand the trade-offs of these different costs. Right. So to give an example, there is something called the cap theorem in cloud computing. And it's a very simple statement. And it's easy to kind of illustrate this with a simple example. So let's say I just have two servers, right? And there is a connection between them. And let's call this server A and this server B, right? And let's say we have a user right, who interacts with server A. And what is happening is this server, let's say it's serving content. So in this case, let's think of it as a single variable like X, right? And then because a single server may be unreliable, we've decided to back it up on another server B. So B also has a copy of X. And now we have user 1, and then we have user 2. And then both users are allowed to like read and write the object. So user 2 can submit a write request to this single variable. And let's say the request is for, first it's for writing 1. So after this, X should be 1. And then there is a protocol that would assume that if a write of 1 is issued at the server B, it needs to propagate to A, right? And let's say initially at this point, let's say the server's value of X is 0 here. And then after this write, this becomes the value 1. And now, depending on how much time it takes for the value of 1 to propagate from the server B to server A, if user A now does a read, right? And then this read might return the value 0, 0, or 1, depending on when you are issuing the read and how long it takes to read. So there is and this is an example of like inconsistency of data, right? Depending on the sequence of reads and writes and the timing and the delay between the servers A and B, the user 1 and user two's view of the system is different. So there is an inconsistency. And if it turns out that user 1 reads before the write of 1 propagates from B to A, then user 1 is potentially seeing a stale value of the variable X, right? Okay, so that's an example of consistency. What is availability? So availability is basically if any user issues a read or write request, then you expect that the server would respond back in a finite amount of time. So, and these are kind of, in some sense, there is a trade-off between consistency and availability, which is why they appear in this gap statement. The P stands for partition tolerance, right? What is a partition? A partition can mean that somehow this connection between A and B is severed, right? So partition tolerance means that even if there is a partition, the system is kind of still operating, even though it may be operating under a more constrained uh, state. It still serves the users. And the purpose of the system in this case is to serve like the values of the variable which is storing here. Okay, so let's think about what is the trade-off here. So the trade-off is, let's say there is a partition of the system. So now A and B cannot talk to each other, right? And that means that basically we say that if the system is partitioned, if P is true, then you can either be consistent, either you have C or A, but not both. Okay, so that's the constraint. Okay, so let's think of it in terms of this simple example here. So let's say the system is partitioned, right? And now, because of the partition, let's say the user 2 is keeping on writing the values. So let's say it keeps writing. So it sends a write of 1 and then write of 2. And then let's say the current state is 2. And now, let's say user 1, the value of 1 from user 2 propagated to the server A, but then the connection got disrupted. So now, in some sense, the latest write to the system is 2, but it has not propagated to A. So now at this point, if we expect consistency, then we need, if user 1 issues a write, issues a read, then if we want the system to be consistent, we can actually return a value for the read of user 1, because if it returns a value, it has to return the value of x equal to 1, which is inconsistent. It's not the latest value. So you can either get, if you want to be consistent, you are not available because you are not able to return a value to the user 1 in finite amount of time. Okay, so that's the case where you are preferring to be consistent and not available. So that's one case. What is the other case? The other case is you prefer availability over consistency. Now, what happens here? In this case, you are available, which means that user 1, once it issues a read, it should expect to get back a result. And in this case, the only result that it can get back is a value of x equal to 1. And we know as a global observer of the system that that is definitely not the latest value in the system, because user 2 has already written w equal to 2, x equal to 2. So it's basically user 1 is getting back a stale value. So it is not really consistent. So in this case, you are preferring availability over consistency, right? So if you prefer availability over consistency, that is usually called an AP system. And an example of AP is Amazon's Dynamo. That's a key value store that prefers to be available, which means that there is always a small chance that if you read the value of an object in Dynamo, there is a possibility that it may be inconsistent or you get a stale value. And then you have higher level application semantics that ensures that you probably keep doing reads, and then you can check for staleness, and then you keep doing it until you get the fresh value or the latest value, right? Or you just, if you have an understanding of the how much time it takes for stale values to get fresh, or if you understand like what is the upper bound of the time it takes for any value to propagate in such a system, then you can just wait for that amount and then or kind of delay your read and then make sure that you get back a consistent value. Okay. All right. So that's all for today. So we just kind of looked at a simple, interesting example of a distributed systems trade-off example. This is called the cap theorem. The cap theorem, it's very simple to state. What's the history? Uh, it was first proposed by Professor Eric Brewer. Uh, he is a professor at UC Berkeley, and he's also been with Google for a long time. And he is the chief architect of Google's cluster systems, and also he designed the Kubernetes system, which is very popular. Uh, the cap theorem, it was described informally, but then it was also made more rigorous by uh, Professor Nancy Lynch and Gilbert. So they wrote a paper that formalized and gave a formal proof of the cap theorem. And in the next lecture, we might try to understand and look at the proof of the cap theorem. All right, so that's all for today. This is kind of a brief introduction to a type of theoretical result that you can see in distributed systems. And we'll continue next time with other interesting topics. So thank you. That's all for today.